Welcome to EPG Pathshala, a gateway to postgraduate courses online. In the previous module, we talked about data communication. Today, we shall discuss about line coding, a yet another module of electronic communication. We know that computer networks are established to communicate information from one station to another. Information can exist in various forms like text, images, numbers, audio and video. In order to communicate these information, we need to convert them into suitable electrical signal, either analog or digital. What to use depend on the type of application we are looking at and the available bandwidth. Computers store information in the form of binary digits. If we want to communicate these binary digits, some suitable digital encoding techniques must be used that will convert these binary digits into some digital signal. Line coding is such a process of converting sequence of binary digits into variation of voltages and currents. When we talk about line coding, we need to understand the various types of line coding and why they are necessary. A good line coding technique can help us in various ways. Firstly, it will remove the DC drift. A long sequence of ones and zeros in the incoming data bit can cause average DC component. Like we all know, DC component cannot travel through transmission medium, so we need to eliminate them. Secondly, a good line coding technique will cause reliable recovery of the clock signal. This is necessary for synchronization between the transmitter and the receiver. So let us now understand the various types of line coding and see their impact on digital transmission. Let us now look at the outline of the lecture. Initially, we shall study the concept of line coding. Then we shall discuss the important characteristics of line coding. Then we shall understand the requirements of the coding. Further, we will look at the popular line coding techniques. And at the end, we will compare the line coding techniques that we cover in this lecture. For long distance serial transmission of data over the coaxial cables, optical fiber or RF link requires the suitable encoding of binary data so that the logic states high and low in the signal can be detected appropriately. Also, the signal during transmission through any type of communication channel, wired or wireless, suffers from attenuation and distortion, which is more severe in long-haul data transmission channel. Hence, for efficient communication, a good encoding technique to tune the signal properties to the characteristics of physical channel is necessary. Information to be transmitted can be encoded in either digital or analog signal using different encoding techniques. Line coding refers to this process of converting a sequence of binary digits, that is bits or digital data, into a digital signal. At the sending end, digital data are encoded into a digital signal, and at the receiving end, original digital data is recovered by decoding the digital signal. Data are encoded in a way that the timing information of the bit stream is maintained and the logic level ones and zeros can be detected. In this module, we shall learn the various encoding techniques to convert digital data into digital signal. Let us now address the various characteristics of line coding. Data rate represents the number of data bits transmitted per second. It refers to the rate at which the signal is transmitted. The unit is bits per second. The data rate should be increased to increase the data transmission speed. Baud rate is the measure of signaling element or symbols sent per second. A symbol in some case would be a binary logic level 0 or 1. In that case, baud rate is equal to bit rate. In other cases, the symbol is one of the several discrete signal amplitudes or phase shifts, each representing 2 or more data bits. The unit is baud. Bandwidth is the frequency range over which an information signal is transmitted. It dictates the amount of data sent over time and influences the choice of digital modulation scheme. Digital signal has theoretically infinite bandwidth, but practically the effective bandwidth is finite. Then comes the DC component. Very low frequencies around zero, which are the consequence of existence of constant voltage level in a digital signal, are known as direct current or DC components. These components significantly induces problems in the systems using transformer coupling, and since most of the transmission channels are bandpass, they may not support the low frequency signals. If the DC component of the transmitted signal is blocked, it will lead to attenuation. Hence, we require line coding of the signal in a way that DC component is absent. Baseline wandering. A receiver will evaluate average power of the received signal and use that to determine the value of the incoming data elements. If the incoming signal does not vary over a longer period of time, baseline will drift and thus cause errors in detection of incoming data elements. A good line coding scheme will prevent long runs of fixed amplitude. Now we shall understand what we mean by self-synchronization. The transformer sends a signal, and at the receiving end, it is required to receive the original transmitted signal. But if the receiver clock is faster or slower, it will misinterpret the incoming bit stream. The difference between the frequency or phase of the transmitter and receiver clocks lead to the loss of synchronization. At the receiving end, the clock signal is recovered from the received data. This requires the signal to contain sufficient amount of transitions, and if sufficient transitions exist, a good recovery of the clock is guaranteed. Such a signal is said to be self-clocking synchronizing, as it contains the timing information in the transmitted data itself. Ideally, digital communication system should be free from any error that gets incorporated into the data during transmission. Hence, it is desirable to implement some modifications in the data, allowing built-in error detection capabilities. This can enhance the receiver capability to detect and correct error. The transmission system used and adopted digital encoding techniques influence the error detection and correction. Now let us understand what we mean by noise immunity. The selected encoding scheme should be immune to noise and external interferences, as we are already aware that any signal during transmission through any type of communication channel suffers from attenuation and distortion. So the requirement is to encode the signal using an encoding scheme imparting high noise immunity. Complexity. An encoding scheme that is complex is costly to implement. Interpretation of any scheme that involves more signal levels is difficult. So the encoding technique should be simple so as to prevent high cost of implementation. Now let us see what are the various line coding schemes that are commonly used. The line coding techniques can be broadly divided into three types. Unipolar signaling. If only single polarity of voltage level is used, either positive or negative, in addition to zero level, it is called as unipolar signaling. Polar signaling. If both positive and negative voltage levels are being used with or without a zero voltage level, then it is called polar signaling. Bipolar signaling is a line coding scheme with positive, negative and zero voltage levels. Let us now elaborate the different categories of line coding. Line coding can be categorized into major three: unipolar, polar and bipolar. Unipolar can be further categorized into two: non-return to zero, unipolar line coding; return to zero, unipolar line coding. Polar line coding can be classified into three: polar non-return to zero, polar return to zero and biphase. Polar non-return to zero can be further classified into two: non-return to zero level and non-return to zero invert. Biphase can also be categorized into two: Manchester coding and differential Manchester coding. Now moving on to the bipolar line coding. We are going to study two types of bipolar line coding. The first one being AMI, which stands for amplitude mark inversion, and the second type of coding is pseudo-ternary coding. Let us now learn the first encoding technique, unipolar encoding. Uni means single. This type of encoding scheme makes use of one polarity of voltage in addition to the zero level to represent logic states. More precisely, positive voltage is used to represent a logic high state and an idle line or zero is used to represent low logic state. Here the baud rate is same as the data rate. In this encoding scheme, since signal of only one polarity is used, it suffers from the disadvantage of having undesirable DC component present in the encoded signal. For long sequence of zeros and ones, there will be loss of synchronization between the transmitter and the receiver. Though unipolar is a simple scheme, but it is not preferred for long-haul communication. This type of line coding scheme is also called on-off keying. Though obsolete now, one of the advantages it has is that it is compatible with TTL logic. As shown in figure, unipolar line coding can be classified into two major types. First one is the non-return to zero or NRZ. Here in NRZ coding, the level of the signal pulse is maintained constant during the entire bit interval. Unipolar non-return to zero encoding scheme is the simplest line coding scheme. Positive voltage is used to represent a logic high state and an idle line or zero to represent logic low state. It has a relatively low bandwidth as compared to its polar counterpart. The disadvantages associated with this kind of line coding, as we discussed while stating features of unipolar signaling, is that the encoded signal has a significant undesirable DC component and is prone to baseline wandering. Also, the encoded signal suffers from lack of self-synchronizing capabilities and has no error detection capabilities. The transmission normalized power for a single bit per unit line resistance is double than the polar RZ. It is costly in terms of power consumption as the signal level remains constant throughout the bit interval and does not make any transition to zero level during the bit interval. Such kind of encoding scheme is generally not preferred for data communication. Now let us see how we represent signal using unipolar NRZ code. In NRZ line coding, logic 0 is indicated by a zero voltage level as shown in figure. Logic 1 is represented by a non-zero voltage level, precisely a positive voltage. The signal level does not return to zero for the entire bit interval during the transmission of a signal. Figure shows the representation of binary data 010, 10110 using unipolar NRZ encoding technique. Let us now see some basic application of unipolar line coding. Unipolar NRZ is a standard positive logic signal format used in digital circuit. Computer circuits use unipolar NRZ internally. Unipolar NRZ is also used in the generation of ASK and FSK signals in the modem. Let us now discuss the next type of unipolar encoding scheme, return to zero. NRZ suffers from lack of synchronization, non-zero DC component and baseline wandering. To overcome the shortcomings of the NRZ return to zero, RZ code was developed. This scheme, like NRZ, makes use of only single voltage polarity with zero to determine the binary logic state. The main advantages of unipolar RZ are ease of generation since it implements a single power supply. The difference between unipolar RZ and unipolar NRZ is that the signal pulse in NRZ stays at a positive value for the full duration of the binary logic 1, while it drops from high voltage level to zero level in RZ in the middle of the bit interval. Therefore, a RZ signal pulse is only half the length of NRZ pulse. This implies that unipolar RZ requires twice the bandwidth of the NRZ code. As seen in the figure, binary logic 0 is represented by 0 level. Binary logic 1 is represented by positive voltage level and a transition to 0 at the middle point of the bit interval. Figure shows the representation of binary sequence 010, 10110 using unipolar RZ coding scheme. In RZ coding, since the level of the signal pulse makes transition to 0 in the middle of the bit interval, the signal is active during half of the bit interval. Now let us discuss the next line coding scheme, which is polar line coding. This line encoding method uses two voltage levels of opposite polarity and equal magnitude, that is, one positive and the other one negative, to represent the two binary states 0 and 1. Also, here the signal level remains constant throughout the bit interval. The average DC component is 0. As the polar NRZ signal has more RMS value than their unipolar counterparts, they can carry more energy. This will aid in better signal to noise ratio at the receiving end. As shown in figure, polar line coding can be classified into three major types: non-return to 0 NRZ, return to 0 RZ, and biphase. Let us now learn them one by one. The first polar encoding scheme is polar NRZ. Now let us see some of the features of the polar NRZ. It uses two voltage levels, positive and negative, of equal magnitude. Here the signal level remains constant throughout the bit interval. The major advantage of using two voltage levels of opposite polarity and same magnitude is that it makes the average DC component 0. As the polar NRZ signal has more RMS value than their unipolar counterparts, they can carry more energy. This will aid in better signal to noise ratio at the receiving end. The drawback of polar NRZ is that it lacks error detection capability when the transmitted signal has a long sequence of zeros and ones. This problem is overcome in polar RZ signals as the signal drops to 0 in the middle of each bit interval. As we can see from the figure, there are two types of NRZ polar encoding schemes: non-return to 0 level NRZL and non-return to 0 invert NRZI. In NRZL, the voltage level determines the bit value. From the figure, we can say that high level voltage plus V represents binary value 0. Binary value 1 is represented by low level voltage minus V. Figure shows how we can represent 010, 10110 binary data using NRZL. In NRZI, transition or no transition in the voltage level determines the bit logic. If the bit being transmitted is at logic 1, there is a transition from one voltage level to other. If the transmitted bit is at logic 0, there is no transition of voltage level. When bit 1 arrives, the signal level is inverted as seen in figure. Figure displays the NRZI coding scheme for the binary data 0101, 0110. If sufficient numbers of logic 1 in the transmitted bit sequence is present, using NRZI, synchronization can be achieved between the transmitter and the receiver. Let us now look at some of the applications of NRZ. The polar NRZ code is used to transmit signals on a computer motherboard. It is also used in fiber-based gigabit Ethernet. NRZL is used in the RS-232 serial port communication. NRZI is used in compact discs, USB, and on fiber-based fast Ethernet, which are running at 100 megabits per second. As shown in figure, the next polar line coding is polar return to 0 RZ. The major limitation of the NRZ and unipolar RZ is the lack of synchronization between the transmitter and receiver clock. This in turn does not allow the receiver to detect the end of one bit and start of the next bit in the received data stream. Also, such encoded signals have non-zero DC components. Such deficiencies are overcome by some modifications imparted to the coding scheme which involves the use of polar and bipolar signals. Let us now see the key features of a polar return to zero RZ encoding scheme. Our polar return to zero has three voltage levels: positive, negative, and zero. To encode a data bit, this scheme requires two transitions per bit interval. Hence, the encoded signal requires higher bandwidth. With the increase in the number of transitions, the synchronization between the transmitter and receiver is good, hence has self-synchronizing capability. There is no DC component and baseline wandering problem in the scheme. One of the major issues with the scheme is the complexity of generating the code, which incur due to the use of three voltage levels. Keeping in mind the deficiencies of this code, it has now been replaced by other efficient codes like Manchester and differential Manchester. Return to zero RZ scheme uses three voltage levels: positive or high voltage, negative or low voltage of equal magnitude, and zero voltage. Each symbol has a transition in the middle. Either transition from high to zero or from low to zero indicates symbol value. This scheme has more signal transitions and therefore requires a wider bandwidth. As seen in figure, a transition from negative voltage to zero indicates logic 0. A transition from positive voltage to zero indicates logic 1. Figure shows how to represent binary data sequence 0111 0110 in polar RZ code. As shown in figure, the next type of polar line coding scheme is biphase encoding. It is a phase encoded code. As we can see from the figure, there are two types of biphase encoding schemes, Manchester and differential Manchester. Let us now understand the features of Manchester coding. This code uses two voltage levels, positive and negative of equal magnitude, to represent logic states. Each bit of data is represented by at least one transition in the middle of the bit interval. During the first half of the bit interval, the signal pulse has zero voltage level, and in the second half it moves to the other voltage level. The code is called biphase as it uses two phase. That is, a signal pulse with a zero phase is used to represent one binary logic, and signal pulse with 180 phase to represent the other. It is a combination of NRZL and RZ schemes. Since each data bit is represented by at least one mid-bit transition, it has the ability of self-synchronization, allowing easy clock recovery of the clock at the receiving end from the data stream. Also, no DC component is present in the encoded signal. The major disadvantage of this type of coding is the requirement of a higher bandwidth, which is almost twice of unipolar or polar NRZ. Let us now see how we represent a Manchester code. From the figure, we can see that the code only uses two voltage levels, positive voltage plus V and negative voltage minus V, for binary logic representation. Binary 0 is represented by a high to low voltage transition at the mid-bit interval. Binary 1 is indicated by a low to high voltage transition, that is minus V to plus V, at the mid-interval. Figure shows how a binary sequence 010 10110 is represented using Manchester coding. It is apparent from the figure that if we have two consecutive ones, the number of transitions will be more. That is from low to high, high to low, then low to high. When data has alternate 0 and 1, then we have less number of transitions, that is from high to low and low to high, amounting to only one transition per bit. Let us now understand the features of differential Manchester coding. Like Manchester coding, it uses two voltage levels to represent logic states. Each bit of data is represented by at least one transition in the middle of the bit interval, as discussed in the earlier slide. The bit value at the beginning of the bit interval determines the logic state. The code also uses phases to represent binary logic states, as in Manchester. It is a combination of NRZI and RZ scheme. It has the ability of self-synchronization. DC component is absent in the encoded signal. It requires twice the bandwidth of unipolar or polar NRZ. As visualized from the figure, Binary 0 is represented by the presence of transition in the beginning of a bit interval. The transition can be from high to low or low to high. If it is binary 1, there is no transition at the start of the bit interval. Figure shows the representation of binary data 010, 10, 110 in differential Manchester coding. Only the presence of transition is important. Working of differential encoding will remain same even if the signal gets inverted. Since there is always a mid-bit transition, it is self-synchronizing and the receiver can easily detect the clock signal from the incoming encoded data. Now let us list the basic applications of biphase encoding. Since this code does not have any DC component and is self-synchronizing, it is used in magnetic recordings. Other applications include satellite telemetry, various optical systems. Manchester is used in Ethernet-based local area networks. Differential Manchester is utilized in token ring network in magnetic and optical storage. Now, moving our focus to the bipolar encoding scheme, we shall now discuss two types of bipolar techniques, AMI, which stands for amplitude mark inversion, and pseudo-ternary encoding. Let us understand the basic features of a bipolar encoding. Here, three voltage levels, positive, negative, and ground, are used to represent logic states. The presence of alternating code in this encoding prevents the buildup of DC voltage in transmission lines. The existence of long sequence of zeros and ones produces no transitions in the data stream, and therefore arises the loss of synchronization. Here, there is no mid-bit transition, hence lesser bandwidth is required. Bipolar amplitude mark inversion, it uses three voltage levels, positive, 0 and negative, to represent binary states. Voltage level for one logic state is at 0 and the other alternates between positive and negative. As seen in the figure, unlike return to 0, 0 level represents binary 0. Binary 1 alternates between positive voltage and negative voltage level, hence it is known as alternate mark inversion. For example, as seen from the figure, if the first one is indicated by positive voltage level plus V, the second one will be indicated by negative voltage level minus V, and the third one will be indicated by negative voltage level plus V, and so on. The figure shows the bipolar AMI code for binary sequence 010, 10, 110. In AMI, long runs of zeros produces no transitions in the data stream and a loss of synchronization is possible. Pseudo-ternary is reverse of AMI. The alternating positive and negative pulses represent binary 0. As seen from the figure, first 0 is indicated by positive voltage plus V and second by negative voltage level minus V. Here, binary 1 is indicated by 0 voltage. Figure shows the pseudo-ternary encoding scheme for data 010, 10, 110. AMI coding was extensively used in first generation digital telephony PCM networks. AMI has long runs of zeros that produces no transition in the data stream, thus may have loss of synchronization. This was solved in telephony by adopting other encoding scheme, which are the improved version of AMI to ensure regular transition in the baseband signal. Based on what different types of encoding schemes we have discussed so far, let us now compare their features. Starting with the bandwidth requirements of each code, unipolar NRZ, bipolar NRZ, and differential NRZ have low bandwidth requirement. Bandwidth requirement of Manchester coding is high, and that of differential Manchester coding is moderate. However, we have seen that Manchester and differential Manchester coding gives very good synchronization facility. That means a signal with long sequence of zeros or ones will not lead to synchronization failure, as the receiver will regenerate the signal without any problem. Unipolar NRZ has high DC component, which makes them unsuitable for long-haul communication, whereas bipolar NRZ, Manchester, differential Manchester, AMI, pseudo-ternary coded signals have no DC component present. Now let us see the representation of binary data sequence 0111, 0110 using different line coding techniques studied so far. From the figure, we can see the data representation using unipolar NR set. Logic 0 is indicated by a 0 voltage level and logic 1 is indicated by a positive voltage level. Then we should see the representation of the same data sequence using unipolar R set. Here binary logic 1 is represented by a positive voltage level and a transition to 0 at the middle point of the bit interval. Binary logic 0 is represented by 0 level. Next we can visualize from the figure again how to represent the data sequence by NR set level and NR set invert. In NR set L, high level voltage plus V represents binary value 0. Binary value 1 is represented by low level voltage minus V. And in NR set I, if the bit being transmitted is at logic 1, there is a transition from one voltage level to the other. If the transmitted bit is at logic 0, there is no transition of voltage level. Then we can see from the figure the representation of data using polar R set. A transition from negative voltage to 0 indicates logic 0. A transition from positive voltage to 0 indicates logic 1. Further, let us see how to represent the same previous data sequence 0111, 0110 in biphase and bipolar coding schemes. In Manchester coding, as seen from the figure, transition from positive voltage level plus V to negative voltage level minus V indicates logic 0. Transition from minus V to plus V indicates logic 1. We can see in differential Manchester coding, transition at the beginning of the bit interval indicates binary 0 and no transition at the beginning of the bit interval indicates binary 1. In AMI, as can be seen from the figure, 0 level represents binary 0. The first one is indicated by positive voltage level plus V and the second one will be indicated by negative voltage level minus V. The third data bit 1 will be represented by positive voltage plus V and so on. In pseudo-ternary coding, as seen from the figure, the first 0 is indicated by positive voltage plus V, the second by minus V and the third by plus V and so on. Binary 1 is indicated by 0 voltage. Now let us summarize what we have learned in this module. We started with the line coding introduction. We understood the necessity of using line coding and what are the requirements. Then we talked about the characteristics of line coding. The major characteristics are data rate, signal rate, bandwidth, self-synchronization, DC component, DC wandering, noise immunity, error detection, complexity, and the cost of implementation. Then we moved on to categorize the different types of line coding. The major categories of line coding are basically three: unipolar, polar, and bipolar. Then at the end, we compared the different types of line coding system and evaluated their performance.